Yesterday we did 7.1 basic or introduction to normal distribution, and today we will do 7.2, which is the real normal distribution. Let's see, let me write it down. The title is Applications of Normal Distributions. Now, I mentioned yesterday that there are zillions, or there are a lot of normal distributions available, but there's only one standard normal distribution. Now, let's see standard normal distribution first. Give me a second. I need to get the picture. Normal distribution curves. This is what we have before. Of course, we don't really see the difference in shape for now. So let's say this is the standard normal distribution. Of course, the mean is 0. Okay, and this z as a random variable is a normal distribution with mean 0 and variance 1. Now, again, don't forget there could be some confusion later on with the second place here. The second place for the normal distribution is the variance. Okay, that's the notation. Now, here's the thing. Here's the thing. Suppose we have now, suppose or let X be normal distribution with mean mu and variance sigma squared. Give me a second. Oops. Okay, suppose we have X to be a random variable with normally distributed with mean mu and sigma squared as our variance. Now then, how do we compute the probability of an event in random variable X? Here's the idea. Here's the idea. Okay, we will start with random variable X, right? Okay, the mean is mu. And let's say this is standard normal distribution, the mean is 0. Now, let's say the effect we want to get is the effect here. Let me use this first. Let's say this is C. And then we want to find the area to the left of that C. We want to find the area to the left of that C. Okay, so let's say the question is probability that x less than equals to C. Okay, that's the blue part here. Okay, now that's the same to find the area under the curve here. So the concept that we had before was the same, that the probability of an event is equals to the area under the density curve of that random variable. Okay. Now the thing is, we don't have the table for non-standard normal distribution. Okay, we don't have the table, so the plan will be as the following. We will actually standardize this C here into normal distribution. Okay, we will standardize that and convert that non-standard normal distribution becomes standard normal distribution. And the conversion will be done by subtracting that C by mu divided by standard deviation. Now that's what we call a C score. Okay, so basically what we will do later from that non-standard normal distribution, I will standardize, let me use red color. I will standardize to be probability of Z in standard normal distribution less than equals to the C score. Okay, and then from there we can use calculator. Okay, now this standardizing process we use Z equals to this C minus mu over sigma. Okay. So later on you will see, to find the area, the yellow area there is the same to find the yellow area here. It's the same to find the yellow area here. Okay, that's how we will compute the probability of an event in non-standard normal distribution. Okay, in fact, I will call that method 1. This is the method I use in my older tests before I require my student to use TI-83 or TI-84. So in my old tests, the way I asked them to compute normal distribution, probability of normal distribution, I want them to use standardizing process first and then use table. That's all time, okay? That's in all time. And I think our textbook still use this method, okay? Yeah, right now, of course, since you converted to standard normal distribution here, then you can just use calculator the way we did it yesterday. Now, I want to teach you another method, method 2, the TI-84 method, calculator method. Okay, now probability of probability of the event x less than equals to c is normal CDF, just like yesterday, normal CDF, okay, negative infinity, the same like yesterday, up to C. The difference is now, instead of the mean equals to 0 in standard normal distribution, now the mean is mu and the standard deviation is sigma. Now, what I need you to be aware is that the notation for normal distribution, the last parameter is variance, while when you use calculator, the last parameter is standard deviation. Okay, not the same. Maybe I use, yeah, not same. One of them is variance, okay, for the notation, for the random variable notation. When you use calculator, the last parameter is standard deviation. Okay. Now, of course, the rest about, for example, about this, the interval, that really depends on the question. Okay, but we basically done with what we need here. Now, okay, let's do example. Let's do an example. A very well-known first example when I teach normal distribution is the IQ score. Let X be normal distribution with mean 100 and standard deviation 15. But this is the place for variance. I put 15 squared. Okay. So for example, X is the IQ score of an adult. So if we look at the density curve, it basically looks like this. This is the mean 100. Okay, the mean is 100, and it's normally distributed. Suppose, for example, part A, find the probability that X, the IQ score of a randomly selected person, is less than less than 130. Less than 130. So we have 130 here. Okay, and therefore I need to find the area under the curve to the left of 130. To the left of 130. So this is, I need to look for the yellow one. Okay, I know the 130, the cutoff, right? I know the cutoff. Then I need to find the area under the curve, which represent the probability. Now, the first method of me computing it, maybe I use the second method first, the way I want you to do it. It will be normal CDF negative E99, that's to replace negative infinity, 130. The mean is not 0 anymore. Right now the mean is 100. And the standard deviation is 15. Okay, this is the way I want it to do. Then you use your calculator. What's my calculator? I think you will get 0.975 as well. Let's see. I use my calculator. Let me change the shading. Okay, so distribution, normal CDF, lower bound, negative infinity, up to 130. So that follows the interval notation that we learned before. The mean is 100 and standard deviation is 15. 0.97725. 0.97725. Right? Did I punch anything wrong? No, I'm fine. Okay. By the way, in old time, so many years ago, I think around 2 years ago, 3 years ago, instead of using the word many, let me use years ago. Years ago, I will ask my student to do it this way. Probability that x less than equals to 130 is equal to, then I standardize first. Okay, z equals to 130 minus 100 over 15. And the C score, I told them, not you. With them, I told them to round it to 2 decimal places. This happens to be a nice number 2. So this becomes probability of standard normal distribution less than equal to 2. And then from there, I asked them to use table. From there, I asked them to use table. And when they use table, I think they will get 0.9773. Okay, but don't do this now. Don't do this now. Don't use this method now. Don't do this now. We have calculator with a much higher, which is faster and more accurate. Don't use this method now. Okay, but the rest basically is the same to what we learned yesterday. Let's say part B. Probability that x is more than or equal to, let's say 90. So basically in words, I'll put more words later on, but right now let's see just notation first and the calculator notation and what it means on the density curve. Okay, suppose, but if we want to see the interpretation here, suppose X is the IQ score of an adult, then this probability of a randomly selected adult has IQ score at least 90. This is equal to, let's see what's the density curve first. So the mean is 100. 90 is to the left of that. 90 is here. Okay, and I need to find the area under the curve greater than 90. Okay, so I need the one to the right of this. I need this yellow color. this is equal to normal CDF, start from 90, ends at infinity, the mean is 100, the standard deviation is 15. Now, please help me computing that using calculator. I don't need to use my calculator. Just use those. I have my table calculator. 74751, that's right. 0.74751. Okay. And how about probability that a randomly selected adult has IQ score between, let's say, between 80 to 120? Okay, you try to do it. You try to do it. So the mean is 100. What I do right now, I graph the density curve, but you don't have to, okay, unless instructed. So this is not part of the requirement for you to show me. It will be nice though, because then you can be able to figure out which region we are talking about. Okay, so we want this region. The IQ score between 80 to 100. Because you use the distribution from calculator, okay, then you need to write the calculator notation. This will be normal CDF from 80 to 120. The mean is 100. The standard deviation is 15. So normal CDF 80, 120, 100, 0.81758. Oh yeah, should be 120. Okay, now that's for if we want to find the probability. That's if we want to find the probability. Now, suppose we want to go the other way around. Suppose we want to go the other way around. Suppose I want to find, for example, find X, the IQ score that separates the top 20% from the bottom 80%. The question is confusing, huh? Okay, because we go the other way around. We go the other way around. What this question means is the following. We want to find what is the cutoff score, what is this X here, or you can also call that C, we usually call that C. Find that X there such that the area to the right and the area to the left is the area to the right is 20%. The area to the right here is 20%. And the area to the left is 80%. So instead of finding the probability, we want to find the cutoff. Okay, so what is that X? What is the X that separates the top 1% from the bottom 80%? So basically, it's this. We need to find that X. Let me change that to C, okay? Let me change that to C. Find C, which is this C here, such that the area to the left of that C is 80%. Now, when we use calculator later on, it's always the area to the left, okay? The area to the left in the notation we use later on to find the cutoff score, okay? We will use the area to the left, okay? So C equals to inverse norm, the area to the left, the mean, the standard deviation. Okay, so this guy here is always the area to the left when you use calculator. This is always, oh, what happened? This is always the area to the left of C. Of course, this is the mean, and this is the standard deviation. Now, inverse norm is located right below normal CDF. Inverse norm is located right below normal CDF. And we can try punching it in. Okay, let me share that with you. Okay, so second distribution, you see inverse norm is right below normal CDF. The area to the left is 80%. Okay, you can use 0.8 or 80%, but I think I will just use 0.8. The mean is 100. The standard deviation is 15. So the 112.62432. So C equals to 112.62432. Did I punch anything wrong? You will use left option. Somebody asked, Professor, my calculator asked for a tail. So it seems like you use TI-84. If it is TI-84, it must be a more advanced one. Okay. Now we always use the left tail one. We always use the left tail one. Okay. We always use the left tail. Now, then this is the cutoff. So suppose for example, if I rephrase that using the IQ as our random variable, then suppose we want to select the smartest 20% of people we allow to go to West LA College. Okay, if your IQ score is not in the top 20%, we do not accept you. You are lucky, that's not the case. Okay, you are lucky, that's not the case. But suppose we actually try to use that policy, then what is the minimum IQ score we are willing to accept into WLAC College, then this will be the number 112.6. Let's say if you round it to the nearest integer, it will be 113. If your IQ score 113 or more, then we will accept you into WLAC College. Okay, yeah, that's if. No, that's not the case though. That's not the case. Actually, the IQ score of students coming to WLAC College, in my opinion, is actually have average of higher than 100. Yeah. Okay, the average IQ score of students coming to WLAC College is more than 100. Okay, I even think it's more than 110. Now the problem is though you can have a high IQ score, but it simply means your brain working fast. But if you have nothing to work on, if your head you don't have enough knowledge in there, then you basically have nothing to use. Flattery for higher rate, my professor score. No, I'm not trying to flatter you. No, it's actually true for every college. Yeah, it's actually true for every college. That's self-selecting situation. You know, okay, you go to SMC, that will be the same case. Yeah, you go to East LA College, that will be the same case. Yeah, because people going to college tends to be somebody who have above average IQ score. I'm not saying that everybody will have above average. Okay, no, that's not what I'm saying. I'm saying that your IQ score has to be above average. On average, it's above average to get to college. Okay, yeah. But IQ score is not everything. So I have seen people with high IQ score and not doing well in their life. What's the point? Okay, so IQ score should not replace your degree, and a degree should not replace your skill. Okay, we don't judge people from their IQ score, just like you don't want to judge people from their degree. Okay, therefore, do not look down on people not having a high IQ score, just like we don't look down on people not having a high degree. Okay, because if you do so to somebody else, trust me, I may do that to you, right? Okay, if that's what you do. But no, that's not what's supposed to be. Okay, I hope one day, our Congress can actually write a law not discriminating people based on their IQ score, based on their degrees, which is actually implicitly already put into the law, but never explicitly said. Okay, there's another one though. There's another one. Believe it or not, this is actually something that we more or less apply in our daily life. Okay, and I have to admit, once in a while, I unintentionally apply this to my daily life. Believe it or not, we do discriminate people based on their look. Have you ever think about it, by the way? Imagine if I were a cashier or a teller in a bank, and then I say, oh, you know what, your face is random, Thomas. Okay, I don't serve you. Imagine if imagine if you have a board saying that we reserve the right to refuse service to ugly people, and Thomas will never be served, right? Because I don't have a chance. I don't have a chance. But
surfing. He's so silly.
Yeah, yeah, that's actually more or less, believe it or not, we talk nicer to somebody who look nice, look handsome, look cute, or look neat, right? Okay, but actually, no, that's not the right way though. We need, when we serve somebody, especially if you have customer service, right? regardless what that person look, regardless what that person wear, you will treat that person the same way. That's what's supposed to be. Okay, I know in America, it's actually, a lot of people say in America it's bad. Trust me, Indonesia is a lot worse in that case. Yeah, Indonesia is a lot worse in that case. Other countries a lot worse. Just put it this way. Don't say, I'm not talking about other people. I'm talking about my own mom, Every time I go back to Indonesia, you know, well, what is our style when you go to a flight of 24 hours? For me to go back to Indonesia, it takes like around 24 hours in total. Now, I will not dress up with a tie. Definitely no, not with long sleeve with a tie. Very likely with a short, okay, with a sport shoes, let's say, and if you see my shoe, it's really old. I mean, you can learn from me about math, about statistics, but don't learn from me about life, okay? Well, now, if I go back to Indonesia and my mom actually saw me, she will always say that, why are you dressed up like this? Looks so junky. You know, and that's how my mom actually look at people at times. You know, it's like, no, you should look better, especially you're a professor, so you should dress up. I say, no, mom. I mean, it's professor is something I do on campus. I do not need to bring that identity with me when I get on plane. You see what I mean, right? Once I get on plane, doesn't matter what's my position on campus. I listen to the captain. I listen to the staff there, and actually that's the law, right? Okay, whatever they told you to do once you're in the airplane, whatever they tell you to do, you have to listen. Okay, of course, they are the reasonable one. We can tell the difference, right? Okay, yeah, regarding the safety of the flight. But see, my mom, for example, just to represent a lot of people especially in my hometown, they see you, they judge you based on what you wear. In fact, to the point of what brand of shirt, what brand of wallet you have, what brand of car you drive. Which is, we are lucky that in America, even though I admit that I saw it once in a while, but it's not something widespread. Okay. Well, anyway, that's a little story time from me. Something quite interesting from different culture though. So back in Indonesia, of course, if I go to Indonesia, I only do vacation. So I don't really need to dress up, but I have to admit, if I ask for some project from a company, I will end up dressing up. You know, I will end up dressing up. Yeah. In America, we don't have that. We don't have that requirement. Okay, let's take a look on some problem from our textbook. We are actually ready to do problems from here. Let me see. Let me grab some. Let me turn off my calculator first, and then I will pick problems from the book. This is chapter 7, section 2. Give me a second, okay? Let's do this. Let's do this first. So in your textbook, that will be number 24 to number 32. This is still notation only. This is still notation only. But before you do the problems, I strongly suggest you to always write down the probability notation. I do expect the way I teach you here, one, of course I teach you to pass the class. Okay, we have department final. Okay, second, I teach you in a way that when you transfer, I expect you to take another statistic class. So I try to adjust with the way I expect your instructor at university level for you to have the foundation you have before you step into their class. Okay, somebody asked me the question, where do I find the solution for the test? You can find it on the test. So you go to that test one, okay, you click on that, the board, right? Basically, but as I know, I have not posted the solution yet. Somebody get perfect score. Somebody get perfect score, and I'm currently asking that person's permission to use her solution instead of using my solution. Let me see. Yeah, I know that person is in here. So if you give me that permission, I would also like you to tell me if you want me to cover your name. Okay, please, I need that explicit permission. I need that explicit permission. Okay, give me a second. I will see if that get that permission because it's not my work, it's your work. Okay, so I need to get your explicit permission for that. Anyway, I have my solution also, but it turns out that this person who get the perfect score did pretty much what I did. The difference is she basically followed the direction, like round to 3 decimal places, and I actually I round to 5, and this person round to 3 when they ask for 3. Okay, I get that person's permission. Let me post it right now. Okay, but meanwhile, you can start working on that problem. Let me give you the direction for this problem first, and then I post it while you work on this. So for this problem here, they tell us a random variable x is normally distributed. So you write it this way right away. X is normally distributed with the mean 50 and standard deviation 7. Okay, that's what you write first. And then on number 24, write the probability notation. And then write the calculator notation. So this will be normal, CDF, 65, E99 for infinity. The mean is 50, the standard deviation is 7. Okay, now let me ask you to do that number 24, and then number 28, and then number 32. It should be a short one. So 1, 2, 3, let's say 5 minutes. Okay, I get the permission. I don't need to cover. Oh, you can see the screen. Oh, I'm so sorry. I'm so sorry. I'm so sorry. Oh. I'm so sorry. I should not share my screen. I'm supposed to share this one, the notes. My bad, 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 my bad. Okay, try to do this first. Yeah, I get permission from our friend Lydia. Thank you, Lydia. Solution. I'm posting the solution now from our friend. I should never use that. Okay, the solution for test 1 already posted. Okay, let me give you 3 more minutes to do this problem, these 3 problems here. Okay, let me start. So number 24, normal CDF 65, E99, 50, 7. I get 0.01606. Number 28, probability that the random variable is between 56 and 68. That is normal CDF 56, 68, 57. 56, 68, 57. I get 0.19062. And for number 32, probability that the random variable is between 56 to 66. That is normal CDF 56, 66, 57. Now, before I do the calculator work, notice that this interval here is smaller than that one, right? It's smaller. So we expect the result here to be less than the probability we get earlier. Okay, this is 56 to 68. This one is part of that interval, right? So if the event is more specific, then the probability, of course, will be smaller. Okay, let's see. That's just a little observation, but if you use calculator since the beginning, you will still get the answer anyway. I get 0.18455. Here it's still only the notation, basically. Okay, let's go on with other problem. Let's do number 40. In my book, number 40 is the Wendy's drive-thru. Wendy's drive-thru. Okay, let me ask you to read that question first. Fast food restaurants spend quite a bit of time studying the amount of cars spent in their drive-thru. Certainly, the faster the cars get through the drive-thru, the more opportunity to make money. QSR magazine, I don't know what's that, studied drive-thru times for fast food restaurants and found that Wendy's had the best time, with a mean time spent in drive-thru of 138.5 seconds. So the mean is 138.5 seconds. And assuming the time is normally distributed with standard deviation 29. So let me start with defining random variable. Let x be the time spent on drive-thru. This x, according to the passage, is normally distributed with mean 138.5 and standard deviation 29. Then part A, what is the probability that a randomly selected car will get through Wendy's drive-thru in less than 100 seconds? Now that's the question in words. Okay, now let's see what's the probability notation. That will be the probability that the time spent on drive-through is less than 100. Okay, you can continue from there later on. Okay, part B, what is the probability that a randomly selected car will spend more than 160 seconds in Wendy's drive-through? So probability that X is more than 160. Part C, what proportion of cars, that's represented by the probability later on, spend between 2 and 3 minutes. And that's actually 120 seconds to 180 seconds. Right? Okay, 2 to 3 minutes. Because the units being used above is, for example, 138.5 are in seconds. They are in seconds. So I need to change the unit to seconds also. Okay, so probability that X will be between 120 to 180. Okay, now in part D, will it be unusual for a car to spend more than 3 minutes? To spend more than 3 minutes. X more than 3 minutes, 180 seconds. Is it less than, you need to compute that first. And then if less than 5%, if less than 5%, then unusual. Okay, now let me ask you to do this problem. Together with your break. This should take you less than 5 minutes. Yeah, this should take you less than 5 minutes. It's because I write the calculator, the probability notation for you already. You just need to do the calculator notation and of course get the answers, right? Together with your break, we will come back at 9:10.
Question real quick, Professor.
Uh-huh.
The standard deviation is squared. So will we have?
Okay, let's start. This is, the first one is normal CDF negative E, 99, 100, 138.5, 29. Where's my calculator? So negative infinity, comma 100, comma 138.5, comma 29. I get 0.09216. Normal CDF 160 E99 138.5 29. I get 0.22923. This is normal CDF 120, 180, 138.5, 29. Okay, 0.6623. 203. And this one here. More than 180. Yeah, 0.07. Oh, it's more than 5%. So not unusual. Okay, because it's more than 5%. Okay, that's for this one question. I would go to, I would like to do more problems. Okay, yeah, but this is where it gets a bit tricky. Before I go on, I have this question from, I get this question from a student about your test 2 on this coming Monday. Thomas, can I use my computer and my phone? So my computer for the webcam and audio, and my phone for me to read the questions, because I write it down, I don't print it. That's okay. That's okay. Second, the question about can we have cheat sheet? I would like to say yes, but here's the thing though. Maybe I write it here then. In test 2, I will allow cheat sheet. I hope that releases some of your pressure. Okay. But no late accepted. Maybe I put it this way. Basically, you need to turn it in on campus, and no time extension. No time extension. I will not give you extra time. Your deadline is, I will post at 7:45. I will post the test at 7:45, and you need to turn it in by 10:15, right? Okay, by 10:15. Okay, now the thing is, I don't care what happened to your signal. I don't care about your internet. I don't care about your campus. You take care of that. Okay. Yeah. What I don't want to happen, and that's what usually happen, is this: you try your best not to study, and study during the test, and you end up not having enough time, and then you complain that either your campus is wrong, the time is not enough, or something wrong here, something wrong there. Good. I give you all the freedom to manage yourself. Okay. But in the end, I just want you to turn it in on campus before the deadline. Okay, so if you know your signal is super slow, okay, if you know your signal is super slow, okay, you will be responsible on that yourself. Okay, don't push it to me, Thomas. You need to understand. No, I don't. Okay, no, I don't, because when I give you this time, when I give you this interval here, basically 2 hours plus 15 minutes, either to print it out or to write on paper, and to scan it, or to take the picture, convert to PDF, and upload it on campus. It's all already put in. Okay, so I do not want anybody to say, Thomas, you know, I forget this, I forget that. No, 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 no. That's enough. Okay. Basically, I don't want to change that anymore, and that's also including your quiz though. You know that you have a quiz due tomorrow, okay? And I get a couple, not only one, I get a couple, I think three students says, Thomas, I tried to turn it in before 8:15, but for some strange reason, you know, if it is strange for you, how about for me? Right? If it's something you don't understand, why do you expect me to understand it while I give you like more than 24 hours to turn it in? So you figure out, okay, you figure out. Okay. Excuses is like only for, I mean, if you have very good excuse, good, go for it. But dude, that's your internet, that's your time, that's the homework I gave you, like even through the weekend. It's hard not to call a BS a BS, okay? Okay, and test 2 will be chapter 5 to 6.3, right? Yes. Test 2 will be chapter 5 to 6.3. To be more precise, only from 5.4. Yeah, only from 5.4. So test 2 material, test 2 will be from 5.4, conditional probability, up to 5.4 to 6.3. Okay, so what I taught you from 7.1 yesterday and 7.2 today will not be in your test 2. Okay, it will be in your test 3. Okay, yeah. So here's the thing. If you take a look on my test, the structure of my statistic class prior to winter 2014, okay, I gave only 3 tests, test 1, test 2, test 3. And test 1 is basically descriptive stats. And then test 2 is probability. And test 3 inferential stats. If I use the cutoff of our class, our textbook, it's chapter 1 to chapter 3, chapter 5 to chapter 8, and then inferential statistics will be chapter 9 to chapter 11. Okay, now then, since 2014, I gave 4 tests. So according to your textbook, if I use that as a reference, test 1, chapter 1 to chapter 3, together with a bit of 5.1 to 5.3, and then your test 2 will be 5.4 to 6.3. Test 3 will be 7.1, 7.2 to 8, chapter 8, plus Bayes' theorem, which is not in our textbook, but I asked that. And then test 4 will be chapter 9 to chapter 11 with chapter 4. I think chapter 4 and chapter 12. I will see if I can go that far. So what happened was this. My test 2, when I gave only 3 tests, the test 2 is actually very, I have a lot of people fail test 2. It's like more than half of the class drop because of test 2. Okay, and it's not because of me. It's actually quite common. It's a quite common situation where once it gets to probability, we have more students drop the class. Okay, now I know that there are some teachers actually quite easy such that they have less students dropping after probability, but compared to test 1, test 2, test 3, or my test 4, we have more students dropping the class because of the probability part. Now that's why then I try in my winter 2014, I split test 2 into 2 tests, and the result was good. And then I tried that again in spring 2014. I tried that again in fall 2014, and the result is actually consistently, significantly better than if I only have 3 tests. Okay, so what happened is this though, to be honest with you. So we finished the material for test 2 yesterday actually, right? Okay, and then tomorrow we will finish the material for test 3. So there's a chance I will move test 3 earlier, or I put more material for test 3. There's a chance that I get your test 3 later on will get into chapter 9. There's a chance. Okay, that's about your test. But for now, worry about your test 2. For a lot of you, you already bombed your test 1, such that the only way you can survive in this test 2 is by doing very well in your test tube. Okay, so please study. We have approximately 1 week to do that, right? Now, let's go back to 7.2. I hope I answered your question. In this, I would do number 44 from your book. Number 44, 7.2. Number 44. Ball bearings are manufactured with mean diameter of 5 millimeter. So the mean is 5 millimeter. And because of the variability in the manufacturing process, the diameters are approximately normally distributed with standard deviation of 0.02. So let X be the diameter of ball bearings. This X is normally distributed with mean 5 and variance 0.02 squared. Now part A, what proportion of ball bearings has diameter more than 5.03? Probability that X is more than 5.03. That one is easy. Okay, we did that before, right? Part B, any ball bearings that have diameter less than 4.95 or greater than 5.05 are discarded. So what happened is this. Suppose I go back to my to the curve. Where's my curve earlier? I need to get my curve from internet again. Well, anyway, let me just graph it. So if we take a look on our curve, the mean is 5. Okay, now they say that anything less than 4.95, anything less than that, or more than 5.05 will get discarded. Okay, so the question is what portion will be discarded. Okay, the proportion or probability of being discarded is the complement of being accepted. Okay, basically not discarded, right? Okay, and the probability that it will be okay will be accepted is when it is actually in this region here. That's the one when we accept. Okay, so that's the probability between 4.95 to 5.05. So this will be 1 minus normal CDF 4.95, 5.05, 5, 0.02. Okay, that's something you can compute. Let me ask you to compute it. Let me ask you to compute it. You compute it, I compute it too. I get 1 minus 0.98758, which is 0.01242. That's the probability of being discarded. Now, why I want to go over this question is because of what happened if we do long run. Now, in part C, using the result in part B, if you produce 30,000 ball bearings, okay, now how many will be discarded? How many should the plant manager expect to discard it? Now that's expectation. That's expectation. Okay, now I want you to realize that what makes test 3 even more difficult when it comes to compounded random variable is because of this. What happened here is I need to define a new random variable. Let y be the number of ball bearings discarded. Okay, now x is the diameter, and that's we were told that's normally distributed. Now this y here, the number of ball bearings discarded, if you think about it, is actually normal, not normal, binomially distributed. It's not normal. So that ball bearing is either the ball bearing, maybe I explain it in a little writing here. The ball bearing is either accepted or discarded. And the thing is, we know that it is discarded at the portion of 0.01242. Okay, now if you produce 30,000 ball bearings, that will represent the number of trials, 30,000 ball bearings. Okay, the probability that it gets discarded is 0.01242. Okay, so this is the n here. That's the n. Okay, this is the probability. That's the p. Now then, the question is, what is the expected value? If you produce 30,000 ball bearings, then how many do you expect to discard? How many do you expect to reject? That will be n times p, which is 30,000 times 0.01242. 30,000 times 0.01242. Don't round it though, don't round it. Okay, don't round it. This is 372.6 is expected to be discarded. Don't round it because this is expectation. Okay, it's not like exactly the number. This is the average. Okay, so if you produce 300,000 ball bearings and this many get rejected, get discarded, then in the end, expect to discard 372.6, expect to accept to be able to use only 30,000 minus that number. So that's 29,627.4. Now, of course, it may be more than this that you can use, maybe less than this. But if when I produce this, I need to tell the machine, you know what, you need to produce a batch, right? A batch of 30,000, then of course, you should not say, Well, you ask for 30,000, I make 30,000 without realizing that some of that 30,000 will be defective, therefore will be discarded. Okay? You know that you need to produce more than that. Okay, you know that you need to produce more than 30,000. You know you need to produce more than 30,000 to get 30,000 at the end that you can sell, okay, or you can use. Okay. Now, part D is even more interesting. An order comes in for 50,000 ball bearings. For part D, you need 50,000 ball bearings. Now, how many bearings should the plant manager manufacture such that after you discard uh, uh, after you discard those that is not in between 4.97 5.03, so this time the requirement is even stricter, okay, then how many the manager should manufacture such that subtracting the expected defect, you still have at least 50,000. Okay, that's the question. So let's see. What is the probability or the portion? We need to first, for step one, we need to find the portion in between 4.97 to 5.03. Let me ask you to compute that. I get the portion will be 0.86639. This is the portion that will be accepted. Okay, now then we will answer the second question, how many to manufacture? So the number of ball bearings we will manufacture, let's call that Y, is binomially distributed. You produce N, the probability of being accepted, the probability that you don't refuse it. This is probability of accepted, the ball bearing to be accepted. Is that now then the expected value, okay, so after you produce N, you want that to be at least 50,000 because that's the order. We expect to have more than 50,000 accepted at the end. Now, then how many should we produce? You see the expectation of Y will be, that's binomial distribution, so it's N times P, 0.86639 times N is greater or equal to 50,000. So N will be greater or equal to 50,000 over 0.86639. I will use the result from my calculator. I get N is at least 57711.03. So at least use, or at least 57,712. I always round it up. Okay. Now our textbook use, I see because I have instructor's edition. Our textbook use 57,711. I think it's quite acceptable because this is so small anyway. Yeah, because that's so small anyway. Okay. Let me try 50,000 divided by 0.86639. Oh yeah, if I use 5 decimal places here, then it will be 0.73. So then if that's the case, then we use 711 here. Okay, but if I use the actual number on my calculator here is 0.8663855. Just try to be more precise. Okay, so if that's the number you use, then you will end up having n greater or equals to 57,711 .02 or 03, what I have for you. I don't know. Now, if that's the case, then you need to have at least to produce 57,704. Okay, so the result that you rounded here, okay, depends on what you get earlier, but always round it up. Okay, in this case, always round it up. Now, I hope from here you see something strange that even though we start with normal distribution, we can actually compound or go on with this normal distribution into binomial distribution later on. Okay. Yeah. Now the thing is, I think our department final don't go into this compound probability distribution like what we had here. But in my test three, you have that a lot. You have that a lot in my test three. Okay. Now I will go on to the next section. I will not do 7.3. Yeah, 7.3 is a heavy use of calculator, assuming normality. So let me just say this for 7.2 suggested homework. 7.2, let me give you the suggested homework first. You can from number 9 to number I think up to number 49. Up to number 49 odd numbers. Seems to be a lot, but it's actually not. It's actually not. Give me a second, I get 2 messages coming in. So is Y number of bearings manufactured or the number of ball bearings discarded? For the previous Y is the number of bearings accepted. For the last one, for the last Y here, the number of ball bearings accepted, because this is the portion that we accept. So let me, I think I need to write it down. Yeah. So let Y be the number of ball bearings accepted. Yeah, because at the end we want to see the accepted 50,000. However, the Y that I use here is different. Yeah. The Y that I use here is the one discarded. Okay, because the probability that I use here is the probability that it gets refused, get discarded, right? Okay. So yes, it will be better if I actually write it down in advance what I use. So it changed from discarded to accepted between C and D. Yes, yes, yes. So if you want, maybe you call this, instead of call this y, call this yd. Yeah, you call it yd maybe to help. Okay. So to just to differentiate between this y and the y that I had earlier, let's call this yc. So I hope your question, it is actually a very, very real question. And to answer your question, you see that it will be a lot better if for every random variable you use, you predefine it first, what it is. Okay, because you see the mistake I make? I didn't define that earlier. I didn't define these earlier such that your view is still with that y, which is the discarded, while my y here that I was talking about is actually the accepted. Okay, so you are right. Your confusion, if you get confused, it's because I didn't clarify at the beginning what's that y is supposed to be. Okay, now if you see in my old test and how I write my solution, for a new random variable I use, I always define it in words. I always define it in words first. What is that? Because I know I will use my solution to teach students in the future semester. Okay, that's how you can benefit from my old test. Okay, because you look at their solutions, and I hope that solutions are clear enough. Okay, now that's for 7.2 suggested homework from 9 to number 49. Now I will jump to 8.1. Instead of calling that 8.1, I will call that chapter 8 consists of two sections, 8.1, 8.2, but instead of teaching you both those sections, I will teach you only a very important one. Okay, very important one, because if you read those two examples, those two sections, they have a lot of examples just to talk about one thing, just one effing thing. And they use at least 10 examples in those two sections. I will just do it one time with one example. Okay, now let's see, this is called sampling distribution. And that's the formal word. Now I want to clarify that sampling distribution actually can be seen as the distribution of sample mean. Okay, the distribution of sample mean. Now, this is a bit hard to explain. Okay, just to explain that this one concept will take us a while, but trust me, if you read the book, it will be even more confusing. So I will just use one example. Let's take a look on the following. Let x be the random variable of, let's say, 3, and then 7, and then 11. And suppose this is equally likely. Okay, be equally likely. In reality, it doesn't have to be equally likely. But I use this as an example to explain what our textbook and what this sampling distribution all about. Okay, so basically the probability of getting a 3 is the same to the probability of getting a 7 equals to the probability of getting 11. Okay. Now, what I want you to do is to do me this favor first. Now, the n here is 3. Okay, there are 3 elements. Now, what is the sum of x and the sum of x squared. The sum of x is 21, right? We basically add them. The sum of x squared is 3 squared plus 7 squared plus 11 squared. I hope you remember that. Okay, that's 9 plus 49 plus 121. That's 130, that's 179. So from here, we see the mean of x. I usually don't use that random variable x as a subscript, but we will be dealing with two different distributions right now. So let me use that subscript x to clarify. This is the mean of random variable x we have above. That's 21 over 3, which is 7. While the variance of that x is 3 times 179 minus 21 squared over 3 squared. That will be 3 times 179 minus 21 squared divided by 9. Divided by 9. I get 10.8. Now, instead of writing it that way, let me write it this way. 96 over 9, let me reduce by 3. I get 32 over 3. Let me just leave it like that for now, okay? When I make it decimal, it may be confusing later on. Now, suppose I want to use calculator to compute the population mean and the population variance. So, let's see how to use our calculator to compute that. Give me a second. So I want to show you how to use your calculator here. Okay, now I want to plug in data. Here's the data, how to plug in data. I go to stats, okay, and then choose option 1, edit. So you see my first column, L1, right? I think I showed you how to use this before. Okay, just to remind you again, then if I plug in number, the data 3, and then 7, and then 11. And I want to see the mean and standard deviation. Calculate one var stats. Please L1. Enter. 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 So you will see the mean. They use X bar, but that's actually population, right? And then we have the sum of X. We have the sum of X squared. Okay. Now, this is the standard deviation if that were a sample, but we are dealing with the population standard deviation. Okay. Now, basically, the thing that I had earlier, 32 over 3, the thing that I have earlier, 32 over 3, this thing here, the one on the right-hand side, the 32 over 3, that's 10.66666 something. If you do the square root, then you will get this number. Okay, but that's not my point right now. That's not my point right now. Okay, that's not my point right now. What I'm trying to do in the next 10 minutes is the following. That's the random variable x. Now we will do the following. Now do sampling of size 2. With repetition. Repetition alone. do sampling of size 2 with repetition allowed. Now, I need you to write all the possible outcomes if you do sampling of size 2 with repetition allowed. So, for example, the first possible sample you get is 3, and then another 3, 3, and then 7, 3, and then 11. That's the first 3 possible, right? Or 7 and then 3, 7 and then 7, 7 and then 11, 11 and then 3, 11 and then 7, 11 and then 11. These are all possible sample of size 2. This is all possible sample of size 2. Okay, that's all possible sample of size 2. Now let's call that sample of size 2. Now then, next, what I want you to do is to get the mean of each possible sample. If these are sample, the first sample, the second sample, right? Okay, what I want you to do is to find the mean of that sample of size 2. That's the notation. X bar is the sample mean, okay? The subscript 2 there is the sample mean of sample size 2. Now then, this will be, for example, this one, 3 plus 3 over 2. That's equals to 3. This is 3 plus 7 over 2. That will be 5. Okay, continue with those. So if you go on, this is 14 over 2, that's 7, 10 over 2, that's 5, 14 over 2 is 7, 18 over 2 is 9, 14 over 2 is 7, 18 over 2 is 9, 22 over 2 is 11. So now you see that my X2 bar, when you do a sample of size 2, if you do sampling of size 2, then the possible means of any sample of size 2 are either 3, 5, 7, 5, 7, 9, 7, 9, 11. Those are the possible mean if you do sampling of size 2. So what is this again? This is the distribution of sample mean. AKA sampling distribution. Okay, this is the sampling, this is random variable for sampling distribution of size 2. Which size 2? Oh, that's confusing right now, huh? Okay, so let's look back a little bit. Let's look back a little bit what we have right now. what we have right now is that first, the x is the underlying distribution. Okay, this x has mean, this x has mu equals to 7, and the variance is 32 over 3. Okay, now x is a random variable, means it has more than one possible value. In this case, x can be 3, can be 7, can be 11. If you do it repeatedly many times, then on average, the outcome will be 7 on average, and the variance is 32 over 3. Now, when I do sampling of size 2, I have different possible outcomes also, right? Now, because it is a random variable, it has more than one possible outcomes. Then we can find the mean. The notation for the mean of that sampling distribution is basically you need to get the average of these numbers. You need to get the average of these numbers. Now, I know it will be confusing when I call it with a certain way that I will do very soon. Okay, but that confusion makes you think, I hope, and try to describe to yourself what it means. So sometimes the wording is tough simply because we try to be more precise. Okay, so what we are going to do right now, find the average here, find the mean here. Okay, and each one of them is sample mean, right? Each one of them is actually sample mean. So what we are about to do next is actually to find the mean of the sample mean. Thomas, you're so mean to make that mean statement. What is the mean of sample mean? What do you mean by that? The word mean is a word in English that has 3 significantly different meanings. The mean in terms of average, the mean in terms of what do you mean, and the mean in terms of you are so mean. Okay, so Thomas, what do you mean by the mean of sample mean? Okay. Sample mean is a random variable. Why random variable? Because it has more than one possible outcomes. Now, because it is a random variable, then we must be able to compute the mean, right? Now, what do you call that? The mean of sample mean. Okay, now what is the mean of sample mean? Let's compute the sum first. The sum of all those x bar is, of all those x bar size 2. When I add them, 15, 20, 36, 43, 63. I get 63. Okay, so the mean of that sample mean of size 2 will be 63 divided by 9 counts. That will be 7. My emphasis will be later on, you see that the mean of the sample mean always equal to the mean of the original distribution. The mean of the sample mean is always equal to the mean of sampling distribution. The variance is where it gets nasty. The sum of sample mean squared will be, so basically I do 3 squared plus 5 squared plus 7 squared plus 5 squared plus 7 squared plus 11 plus 9 squared plus 9 squared, I'm sorry, plus 7 squared plus 9 squared plus 11 squared, or you can just use your calculator. Okay, when you plug in those 9 numbers into the data, right? But now I don't want to do it that way. So 9 squared plus 5, I'm sorry, 3 squared plus 5 squared happens 2 times, plus 7 squared happens 3 times, plus 9 squared happens twice, plus 11 squared, I get 489. So the sum of x bar squared is 489. Then the variance of the sampling distribution with size 2, ooh, there's a lot of notation there, will be 9 times 489 minus 63 squared over 9 squared. I get 432 over 81. If I reduce by 9, I get 9 here. 432 divided by 9 is 48. And then I will reduce by 3. This will be 16 over 3. Now you will see that the result here is basically this number divided by 2. Divided by 2. Not always by 2. To be more precise, divided by the sampling size. In this case, we sample the size of 2. The conclusion that I want to make here, is the following. Let x has the mean mu sub x and variance sigma squared x, then x bar n, sampling distribution of size n, has the mean is equal to the mean of the original distribution, yet the variance of size n is the original variance, divided by n. This is what you need to memorize until tomorrow. I mean, tomorrow we will work on this. Okay, I have to stop here. No homework yet so far. For this section. Tomorrow I will continue from this, and then we go on to chapter 9. Okay, see you then tomorrow.